Hello, everyone. Welcome to Saturday's extra lesson. I think you must have realized I sent out maybe more than a week, the homework more than a week ago. From chapter 6, assignment 1 and 2. You can go to the Google Classroom to check these two assignments. Exercise 6A. The application on tangents on curves. The three questions are completely different. The first one is a logarithmic function. This is a normal function, being an explicit function. So the differentiation is very, very easy. You only have to find out the point of contact. You can find A first and then find B. And then you can set up the equation. The equation has log 4 in it, but that's okay. You must keep log 4. Question 21. This is what I say. This question is the hardest because you have to find the point of contact and the slope at the same time. During the lesson, I talked about two different methods. One using delta equals 0, the other one using differentiation. In your homework, you must use the method of differentiation. You mustn't use the delta method. Okay, so some of you have to redo. The two equations you set up are this one. Okay, where is it? This one. This is from point AB lies on C. Another one is the slope equals slope. The left-hand side is the slope from the derivative. The right-hand side is the slope from the definition. That means slope between 2 points. And then you can find A and B, and then set up equation. You find A and B. Find A, then find B. Separately. One of you put them all together. You cannot. You must say A is this, B is this, A is this, B is this. And then you write the equation. Question 22. This one is, I think the most difficult part is the implicit differentiation part. And some of you still haven't fully mastered this technique. And in your homework, I gave you suggestions. Please seek help. Please seek help, okay? The implicit differentiation is difficult, but once you overcome, you will find it very easy. So that is dy dx. You see, dy dx has y in it. That you need to find the point of contact, and it's given the point of contact is the x-intercept. So you will find the x-intercept. This is the x-intercept. Now remember that x-intercept is a value, not a point. Intercept is a value, not a point. So this one, I don't call x-intercept, I call the intersection, intersection with the x-axis. And then you will find the tangent, the slope of tangent using the first derivative. Now, some of you didn't substitute the value of x and value of y at the same time. You cannot do that. What do I mean? Now you see this expression, the implicit expression, has x and y both in it. If you want to find a derivative, I mean the value of the derivative, you must put in the value of x and y at the same time. Some of you only put in the value of x. I think in the case, some of you only put in the value of y and left out the value of x. So in this step, some of you only wrote, oh, the derivative is 1 over x. It's not 1 over x, it's 1 over 5. Cannot be 1 over x. Doesn't work that way. When you do substitution, don't substitute half. You have to go full on substitution, x and y at the same time. And then the final answer. The second assignment. The second assignment, when you answer the increasing part, the increasing interval, you answer the close interval. I mean, you close at a point where the change of the sign happens. So this one is inclusive of 1 over 2 to infinity. At infinity, it's open. Okay, or you can write this. Oh, sorry, I wrote it wrong. It's from negative infinity to 1 over 2, closed interval. At infinity is always open. Do not write close. This one, you can write this inequality or 1 over 2 inclusive to positive infinity. Okay. Now, question 10. This step must be shown. The listing out the signs of the first derivative must be shown. And then 1 is maximum, 1 is minimum. Minimum point, I mean. I shouldn't say maximum. 1 is a maximum point. 1 is a minimum point. In fact, I shouldn't even say this. I should say 1 is a local maximum point. 1 is a local minimum point. That's the full name. Okay, but sometimes we just don't say local. But we mean local all the time. In local. Question 16. In question 16, this is a trigonometric function. So you practice again how to solve trigonometric equation. The stationary point is pi over 2 over pi over 2. And this time no one wrote 90 degrees. That's very good. And then you answer pi over 2 is neither a maximum point nor a minimum point. Or you can say it's a saddle point. 20. Now 20 has 2 problems. One being this range is randomly added. Some of you didn't consider this. Some of you only wrote x is smaller than e and didn't realize that x must be greater than 0. Now, I guess it's not a huge problem, not a huge problem here because you wouldn't substitute a negative value in it, right? Otherwise, you get undefined. You would put in some number smaller than e, but greater than 0. But later on, you must realize that it's undefined when x is smaller than 0. So there will be nothing on the curve on the left-hand side to the left side of the y-axis. What do I mean? Just like the log graph, because the log graph, for example, this one, the y equal log x, this graph is undefined when x is smaller than or equal to 0. So the graph doesn't have the left half. It's blank on the left. Now, also the second problem is the local maximum. During the lesson, I didn't didn't make it super clear. Now, when I say maximum, I mean the value of y at the maximum point. So when you answer maximum, you answer only the y value at the maximum point. In this case, is 1 over e. That's all. That's all. I know it's a long time ago, so you probably need more time to remember what you've done. But I think as soon as you look at it, it should be quite clear. Some of you didn't hand in your work. You should hand in your work. Now take out the M2 notes. If you don't have the hard copy at home, you can always use the soft copy. This is on page 39. Why does the notes has 39 pages? I don't know. And this classwork, last time we didn't finish. Okay. I saw some of you have already completed, and it was quite, it's correct, but I still have some points to make. Now, in this question, if you look at part A, part B, A to E, basically, A to E. Okay, it's not this one. Oh, not this page, sorry, not this page. Wow, I was wrong. It's the next page. This page. Page 41, sorry. Because I'm using another device, I forgot that we already explained the example. Now we're talking about the classwork. So page 41, this one. The reason I want to talk about this question is because the parts from A to E, you may think, oh, there are so many parts I need to do before the sketching. The information I have found must be enough for me to plot. But in this case, it's not so much, not enough information, because you look at the final, this graph, you only have 3 points found. So you have to sketch the whole curve. It's not easy. It's not easy. Also, if you pay attention, you will see that through A to E, you do not look for the second derivative. So you do not know the concavity. You also have no idea about the point of inflection. Maybe there are something there, but you don't know where they are. So that's why the graph is more difficult. You have to use your imagination and some side evidence to plot the whole graph. I'm showing you how. So with these 3 points found, we know that this is a minimum and this is a maximum. And this is just some random points found in part A. We don't even know how this point can help us, because this point is not anything. It's not point of inflection. It's not maximum minimum. It's just a random point that this line is passing. Okay. However, because we know the minimum must be lying on the concave up curve, and this one must be concave down. Concave down. This one, concave up. So we know that in between there must be a change. Okay, so you can use your own judgment, and it's allowed to decide where the change is. For example, if I put the change here, This is the crossing. Maybe I put this, the green one. Ayo. Wow. Okay, the green, okay? And then I will plot the concave down like this. Make sure it passes through this point, and then concave up this way. I can decide where it is, okay? Now I can also put it somewhere else. Maybe I erase this and I put it somewhere here. That's also allowed, like this. Now it's not easy to plot, but I can put it there and do this concave down, concave up, you see? As long as I can make it work, although this is obviously not the correct point to put. Now I think it's more reasonable if it's more to the left. But you know what I mean. If the point of inflection is unclear, then you must decide on your own where you want to put it. Now here I put it here. I think it's more reasonable if it's there. Okay, so there is a change. There is a change. Okay, now how about at infinity? Now we know that at infinity, this will go to this line. Okay, but is there a change of concavity somewhere else? Let's think about it. If this is concave down forever, if this is concave down forever, this line will go through y equals 2 again. But in part A, we already know the curve only intersect y equals 2 once. You see, that's what I call a side evidence. Now, does it go down infinitely? No, no, because we know that this curve does not pass through y equals to 2 twice. So only once. That means I need to make it stop somewhere and then go to y equals to 2 indefinitely and make y equals to 2 a asymptote. Okay, so because I need to do that, there is a change of concavity here. Now, maybe you didn't notice, but there is a change of concavity here. But you don't know where it is, so you can decide, you have some freedom in deciding where it is. But if you're hardworking enough, you would do the second differentiation and find out. Then you have a perfect graph. But it's not necessary, okay? In this question, it's not necessary. We allow you to have this freedom, okay? Similarly, on this side, there is one as well, but we don't know where it is. We know that this graph does not go through y equals 2 again. So at some point, it needs to change the concavity. Like that. Is that okay? So use all the information we found through A to E. We know the maximum, we know the minimum, and we must imagine there are 3 points of inflection. So I think the classwork is more complicated, is much more complicated because you need to use side evidence, much more complicated than the example. Now, if you go back to the example has everything found. The example has everything found because the change of concavity here and then change of concavity. Now, let me point out the change of concavity. It's quite clear where it is. You see? Do you have any question? Now, when I hear no reply, I just imagine maybe I didn't turn on my sound, but I do have my sound turned on. So there is no question there. Let me know. Let me know. I think that's it, isn't it? This is extra example now. From the textbook, you are done. You're done. But maybe not done from my lesson. Another graph. Consider the graph. Find everything. Okay. When this equals 0, x equals 3, x-intercept is 3, y-intercept 12. First derivative, d high, low, d low, high. So 4x, 8. Isn't it? I just want to know if I'm correct or not. Second derivative. Let's differentiate twice. So negative 16. You see, I do not use quotient rule. Now the signs. The signs, 1, x is smaller than 1, x is bigger than 1. Now the reason I put 1 there is because 1 is undefined. So smaller than 1 positive, bigger than 1 positive. The function is increasing for x is smaller than 1 and x is bigger than 1. Can you say all real numbers except 1? No. Later on, I will tell you why. You must say, oh, on this half, it's increasing. On this half, it's increasing. You cannot say everything except. We will tell you why later. C. First derivative equals 0. 8 equals 0. There is no solution. There is no way 8 can equal 0. So there is no turning point. There is no stationary point. There is no stationary. There is no turning. Okay. Now, how about the second derivative? Solving the second derivative equals 0. We also have nothing. No solution. And this one is undefined when x equal to 1, right? We also need to consider where it's undefined. So when x is smaller than 1, x is bigger than 1, it's smaller than 1 positive, bigger than 1 negative. Okay. But if you look at that, then there is a change of concavity. But since this is broken at x equals to 1, so there is no points of inflection at x equal to 1. But there is a change. This will be helpful. Okay. You may say, oh, why do I need it? There is nothing there. Why must I check the concavity? It's going to be useful. Otherwise, you have nothing. Finally, the asymptotes. First, the vertical asymptotes. Vertical asymptotes at x equal 1 to the left. X equal 1 to the left. That means I need to substitute 0.9, 0.99, and so on. Substitute x equal 0.9. Okay, put in, you get positive infinity. This one, negative infinity. I actually did the substitution. I didn't make it up. You don't say, oh, Ms. Chen, you've done so fast. Do you have any? I don't have shortcut. I did that in my head. So x equal 1 is a vertical asymptote. Okay. Now, how about horizontal asymptote? You can do the long division. This is 4x minus 12, x minus 1, so 4x minus 4, minus 8, so minus 8. So this is equal 4 plus 0 equal 4. So y equal 4 is a horizontal asymptote. Now let's move on. the sketching. Now we know the asymptotes. We know the x-intercept, y-intercept. But unfortunately, we don't have any turning. We don't have any, what do you call it? We don't have any turning. We don't have any points of inflection. Then how do I even start? How do I, after so much calculation, I don't know where to start. You start at these evidence. First, we figure out at the left-hand side of x equal to 1, it goes to infinity. So here I will plot a very high point here. And then I will connect them like this. This side, because on the right-hand side of x equals to 1, I also have negative infinity. So I will put a point very negative and close to x equal 1. And then I will connect this way. Okay. And remember, there is no turning. So if it's increasing, it's always increasing. It doesn't turn. It doesn't turn. If it's decreasing, it's always decreasing. And for this function, we know it's increasing on the left. We know it's increasing on the right. So that's how I'm going to make it this way. You know what I mean? You know what I mean? Now you can see all the evidence, they are put together. For example, increasing on the left. Do you see increasing on the left? Do you see increasing on the right? And you can see why I don't say increasing on the whole thing, because from here to here, it's not increasing. There is a jump from positive, it's not positive, from a high value to a low value, there is a jump. But it's increasing on the left and increasing on the right. Okay. And also about the concavity. On the left, it's concave up. On the right, it's concave down. That is consistent with our finding here. Positive second derivative. Concave up, concave down. And also, there are no turning points. Do you see? It doesn't turn. There is nothing. Doesn't turn. That completes this graph. Sometimes you have less to work with, but you don't. I know that the point of the maximum point and minimum point and points of inflection, they are very strong evidence, and you can always plot a lot of things around it. But essentially, you can derive something very important information from increasing, decreasing. Now that's very strong. Increasing, is the function increasing or decreasing? And also the concavity. Concavity can tell you a lot about where this curve goes. Okay, so this is the question about concavity and the other things without turning points. Extra example 3. Consider the function. Find everything. Part A. The graph is undefined at 3 or -3. So the domain is all real numbers except 3 and -3. First derivative, d high, low, minus d low, high, divided by low square. And the key to simplify is to take out. So I take out 2x, I have negative x squared plus 9 minus 12 minus x squared. Okay, so I'm left with 6x. The answer is there. Otherwise, you spend a long time. Next one, second derivative. So d high, the negative sign is taken out. So I don't have to worry about the negative sign. So it's d high low minus d low d low is the composite function. I need to use chain rule so you can see I derive using two different rules. D low high, and then I simplify. Now when simplifying, I also take out x squared minus 9. I just skip that because we've done so much. I trust you can do it. Part C, y-intercept found. You must do that yourself. X-intercept found. Okay, and then found. Turning points, 0. Okay, and second derivative test. I think I'm getting a little bit lazy here. I use the second derivative test. Anyway, let me put in 0, 0, 0, 0, and it's negative. It's negative, meaning it's concave down. Concave down, meaning it's a positive, it's a maximum point. Moving on, second derivative. Now, to find the second derivative, I will further factorize, and I found no 0 point, but it's undefined at 2 points. So I want to check for the concavity. So with negative, it's negative, negative, positive, it's positive, sorry, positive, 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 negative, positive. So it's concave down, concave up when x is smaller than -3 and x is bigger than 3. Now, when you answer concave up, concave down, you don't include the -3 and 3 because they're undefined. You can't include them. And then when the concave down is between -3 and 3. Okay, finally, the asymptotes. Asymptotes at 3, this one is 3 to the right. This one is 3 to the left. 3 to the right. 3 to the right. This is a positive one. Yes, it's positive. 3 to the left, it's negative. X equals 3. -3 to the right. Sorry, -3 to the right. So positive, negative. I need to be careful because -3 to the right is -2.9. So -2.9 to the right, that's positive divided by positive, negative. It's negative infinity. And this one is positive infinity. Okay, another one. Now, how about horizontal asymptote? Sorry, this is -9. I changed the equal to minus. Wow. Negative x squared plus 12, x squared minus 9, so -1. Negative x squared plus 9. Then you have 3, so you have 3 left. So this one minus -1 is 3, and then the limit at infinity equals 0. So y equal -1 is a horizontal asymptote. Now the curve. Now the curve. Now the curve. We know, do we have a turning point? Yes, we have a turning. We have a maximum here. Okay. And this is just the point passing. This is a point passing. Okay. And then there is no change of concavity, the whole curve here. Nothing changed here. No change. But there is a change at -3. This must be going up. You see, this side is concave up, and this in the middle is concave down, and on the right hand side is concave up. At infinity, it goes to y equals to -1. So here you can see it gets closer and closer, and this it goes closer and closer like that. This is also consistent with the limits we found. Like to the left of -3, it goes to positive infinity, remember? This side negative infinity, and this one negative infinity and positive infinity, you see? It all works out. Do you have any question? There's no exercise, so this time I don't know. You just follow me. In the homework, I will ask you to plot a similar graph like this. Maybe just once. Maybe just once, because you've never done it all by yourself. Next one. Is this the last one? I really hope this is the last one. Yeah. Okay. Now, as we go on, you can see the degree gets higher and higher. I don't know if you notice. This is a cubic divided by a quadratic. And if you go back, this one is a quadratic divided by quadratic. And this one, linear divided by linear. This one, quadratic divided by quadratic. I guess the hardest must be cubic divided by quadratic. Is there a 4, like power 4? I don't know. I don't know. Technically, we can solve everything. Technically, but because the limitation on the time, usually will give you like a 2 or 3 degree, and that would be okay. If you can solve this one, theoretically, you can solve everything. So that's just a test. If you can really master this concept. So consider the function f of x cubed divided by square and the graph of y equal f of x, the domain and everything. Undefined. All real numbers except 2. Y-intercept, x-intercept. Okay. First derivative. Wow. Well, I have to do it myself. 3x minus 6 minus 2x. Okay. Okay, I'm doing testing. I hope I'm right, huh? I don't want to make a mistake. Let me check. Negative, 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 positive. Positive. Negative, negative, positive. That's okay. Just to make sure, huh? Just to make sure. Now 0, 0, obviously it's a saddle point. And x equals 6, y equal the value 6 cube divided by 4 squared. 13.5. Oh, it's there. It's there, 13.5. And that one is a maximum. Oh, sorry, minimum. I always need to check up. Negative, 0, positive is a minimum. There are no maximum points. Okay. Moving on, second derivative. The second derivative is based on my first derivative. And my first derivative is x minus 6 divided by x minus 2 cubed. Okay. Now to differentiate quicker, I will expand first. X cubed minus 6x squared divided by x minus 2 cubed. Okay, I think this is easier. So I do d high low this way. And d low high. Okay. And with the simplification, I need to be very, very, very careful. So I take out 3x. I'm left with x minus 4, x minus 2. And take out 3x, x minus 2 square. Take out x. That is x squared minus 6x. I hope you agree with me. I need to check twice. I take out 3x, x minus 2 squared. In the first term, I'm left with 3x taken out, so x minus 4 times x minus 2. That's correct. For the second one, I'm taking out 3. I'm taking out x minus 2 squared. I'm also taking out x, so x squared minus 6x. That's correct. That's correct. And then after calculation, I think this equals to 8. This equals 8. So that's why in the final answer, I have 24. Okay, and also x minus 2 to the power 6 is reduced to x minus 2 to the power 4. There's no shortcut, guys. There's no shortcut to the differentiation anymore. Solving. Okay, there's 1 point. And we already know it's a point of inflection. Now, I said before, a saddle point is a point of inflection. So we don't have to check anymore. It's already checked. Okay, now how about x equals to 2? It's undefined. I also need to check that. So I guess I will check the whole thing then. I will check the concavity. This is what I do. So smaller than 0, negative, bigger than 0, positive, positive. Okay. Now we know that at x equals to 2, there is nothing there. So at x equals to 2, there is no point of inflection, but there is a change of there is a break. There is a break. I can't say there is a change of concavity, but there is a break. Before x equals 2 is concave up, the other side is also concave up. Later on, you will see. Now the asymptote. At left to x equals to 2, positive infinity. At right, x equals to 2, positive infinity. I actually did the substitution. So x equals to 2, mass. It's a vertical asymptote. Now about the oblique asymptote, x cubed divided by x squared minus 4x plus 4. Okay, and then I'm left with x cubed minus 4x squared plus 4x squared minus 4x plus 0 plus 4x squared minus 16x plus 16, 12x minus 16. So here it's x plus 4, 12x minus 16, and x plus 4, 12x minus 16, x plus 4, 12x minus 16 equals 0. So y equal x plus 4 is an oblique asymptote. That's correct. Now the curve. Now the curve. This is a maximum. This is a minimum, sorry. This is a minimum. Okay. And this is the point of saddle point. Saddle point. How do I call it? It's saddle point, positive, positive. And before this, it's concave down. And after this is concave up. Let me draw it draw it better. This is concave down, and this is concave up this way. A saddle point. Learn how to draw a saddle point. Concave down and then concave up. And the slope is positive, 0, positive. So looks like this: positive, 0, positive. But you make it a curve. Curve. Concave down and then concave up. Okay. And also to the left, it goes to positive infinity. That's what we found. Okay. To the right, it also goes to positive infinity. And also this. Okay. On this side, it goes to the line, goes to this line like that. That's my finding. Because that's my finding. Now, if you go through A to E, you find that it's all consistent. Saddle point. Around, very near the asymptote. Left-hand side infinity, right-hand side infinity. Concave up here. Concave up here. Concave down here. Now, look. This table. This table. Concave down, concave up, concave up. You see, negative, positive, positive. And then here, concave down, concave up, concave up. So that's it. That's it. Now this graph obviously looks a bit different from the examples from the textbook. This is because their degrees are different. I think learned the knowledge you learned from the compulsory part should tell you that for different degrees, the graph should look different. Don't you think so? If it's degree 1, it's a straight line. If it's degree 2, it's a parabola. So this one is a degree 3 divided by the degree 2. So the curve looks very strange. Okay. Do you have any question? This is the 3rd time I'm asking. Nothing? I hope you learn this relatively easier this time. The reason I say so is because I spent quite a long time to put in all the steps you need, and then to help you with the plotting for the first time. I know that later on you have to do it all by yourself, but I think with this guidance, you should feel more confident. You should know of this. You should expect this is what you do. Even though it seems very long now, it shouldn't. Later on, when you are just you practice enough, and then you will be there. It's not like, oh, this is, unless you don't understand at all. Okay, unless you don't know what I'm talking about. Because I feel that I'm repeating. I feel I'm repeating, but if you don't know what I'm talking about, then me repeating is not going to help you. Then you may need me to, or you need someone to rephrase it for you. Maybe say it in a way that you can understand, and we can try. We can try. It's not something unattainable. I think, because the values can always be tested, right? In my opinion, if you understand what the curvature means, what the first derivative should mean to you, what the second derivative should mean to you, then you will get there, I hope. The other day, Pearl was the thing on me making the material for students to revise. I hope you don't feel that way. I hope that you don't feel that I'm asking extra from you, asking you to fill in and to follow exactly what I want you to follow the step exactly. I have no better way to tell you what to do. And I feel that you need to learn from me. I feel that you just need to get into my head, and then it seems easy to you, because it seems so easy to me. I hope it helps. Let me know. But I will see when you complete the homework. I will see. And in your homework, let me say, you make the graph as good as possible. And don't draw a very small graph. Just use an entire page for it. Okay, here I'm using half of the page. You use the entire page for it. And it's okay. It's okay. Give me 3 minutes and we will come back in 3 minutes.